So today I'm going to talk about logarithms with finite fields. And so they're a little different, but they're mostly the same as logarithms that you've seen before, whether it's over various bases, probably with the real numbers, even with the complex numbers. But they're very important. I mean, the discrete log problem is a very standard problem that is used in cryptography for public key cryptography. If you learned what Diffie-Hellman is, you've probably learned it based on the discrete logarithm assumptions. Although, if I recall correctly, you need to have a special Diffie-Hellman assumption, which basically says we assume Diffie-Hellman is difficult with discrete logs modulo some large prime. And then I'm going to talk a little bit about a logarithm problem, which I planned to have gone over how to solve a basic number theory problem that I saw with logarithms, but in trying to work it out, even with a friend, found that this basic number theory problem was more involved and would have probably doubled the length of the video, and so I'm not going to do that. And then we're going to talk about slide rules, because why not? But before we get to all that, we have to start with exponentiation, because that's really what logarithms are. It's exponentiation. And so if I have some finite field of order q, where q equals p to the n, well, I know that the units, math BBF, I can multiply. Well, before getting to that, I can multiply inside my finite field to get to a squared, but I can do this an arbitrary amount of times, and so I can form a to the n just by multiplying repeatedly. But a to the n is, for any positive integer, is almost too much information, because we know one thing. We know that the units, math BBF q to the star, the non-zero elements, are a cyclic group of order q minus 1. And so that means that if I raise a power, if I take any element, a in fq2, because this holds for 0, then a to the p minus 1 equals 1. Well, that's not true. It equals 1 on the units. Let's say on the units to the est. And on 0, it equals 0. But that means we can reduce this further, because we start out with exponentiation where we're taking powers of integers, and then we specialize down to integers modulo. I write p minus 1 here. I really should write q minus 1. Let me fix that. Q minus 1. And so what we get is that exponentiation, really, once we've chosen a base, some element which we usually call g, is a map from the integers mod q minus 1. I'll just write mod q minus 1 back to our field, math BBF q. And hopefully our g is non-zero or primitive. Okay, that's interesting enough. And this already diverges a little with the stories of logarithms you're used to, probably. But I mean, if you started out with the real numbers, it doesn't really directly diverge that much, because logarithms start with you take these x to the k's, and then you use essentially the topology of the real numbers to show that, once you've shown, also using the topology, that these nth roots exist, you can take rational approximations to be able to get, an exp that is very nice, that goes from the real numbers to the positive real numbers, underscore greater than 0. That your exponential doesn't need to be restricted to just integers. You can do your exponential from some base. So I should say exp underscore, you choose some base, it's probably e, and you get this order-preserving isomorphism of abelian groups between these two guys, which is very nice. And so you might think with finite fields, well, can we raise to the power of our own finite field? And the answer is basically no. And part of that is that, with finite fields, once we cut out 0, it's almost as good as it could be the case with exponentials and finite fields, because it actually flattens out the finite field. It gives an isomorphism of the exponential expresses when we take g to be a thing called a primitive element, this is how we define a primitive element, is where exponential gives this isomorphism between CQ minus 1, the cyclic group of order Q minus 1, and FQ star. And that kind of flattens out our field, because a field of order Q doesn't really naturally have a linear order. I mean, it's, z, the integers mod Q is not a linear order, or the integers mod Q minus 1 is a linear order, but it's closer. It wraps around, and you can sort of maybe call it a circular order. And so about as good as we can, we get the exponential. And so the next natural thing is like, well, once we take these exponential, we just take the inverse. So logarithm, which oftentimes, and in fact in mathematics in general, we don't write the base of the log. Because oftentimes the base of the log doesn't really matter. Because it just then it just differs by a constant factor. And that's the same with logarithms over a finite field too. Except in this case, mathematically, whereas in the case of real numbers, we'll just say real numbers, not even talk about complex numbers, because there are other complications with logarithms and exponentials with complex numbers, which could be its own video that really gets into the geometry of complex analysis. But we're not doing that now. When I take, say, like log a of x, now I'm working over the real numbers. And I compare that will always be equal to some constant c times log b of x. There will be some number, and you can work out which number by an exercise, and it'll be the same, and that exercise will essentially be the same exercise, algebraic exercise, that the same thing happens here. But when you're in the case of, like, let's pick a specific q. Let's pick q equals 9. Then z mod q, or I keep switching notation, which is a bad choice. Our units will have size C8. And so if I pick some root g, which generates where the powers of this non-zero element generate all the elements of the units, I can then take g squared. And this will not generate all the powers of the units. In fact, the discrete log will not exist for half of them. And that's not something that happens in this case. So, if I take now we're working over, I guess I should write it differently. FQ, this is bad notation. Nobody writes this, by the way. We take the FQ log underscore g of x. This will be defined for every non-zero element of our field. In this case, let's call it the F9 logarithm, if g is a primitive root, which I haven't computed a primitive root, so maybe you should deride me in the comments. Either find one and then bully me and say you should have come prepared with an example. If I take log g of x for any element of FQ star, I'll always get, there's always an answer. There will be some element of z mod pz where if I take a g to that power, I'll get x. But if I do the same thing, and now I try to do math bb f9 log underscore g squared of x, this will only be defined, it will only be defined on this group, fq ast squared. Now this is not perfect notation either, because it's a little confusing, and it's not even perfect notation because it doesn't compile for me. But this will only be defined on the subgroup of C4, the unique subgroup C4 of C8. Because for most of them, there is no answer of, you can't take a power of g squared and get an element, only half of them. And so this is something that you have to be careful about, And we say an element G in some arbitrary FQ. Again, I should write F9 here because I'm keep vacillating. An element of FQ is called primitive if G generates math BB under multiplication. And so if you take primitive logarithms, and if you ever see someone working with finite fields and they write log and they don't give a base, it means just take some primitive root. If you're working in a computer algebra system where you are working modulo Conway polynomials, the element x inside why can't I write this? Inside FQ, well, basically fp of x mod f of x, where f of x is a Conway polynomial, the element x will be a primitive root. And every other primitive root will be related to x by some power of some n in math BBZ. This is where I actually have to write it this way. I can't write it the other way, to the s, by a unit in here. Every single other primitive root, I can take a power, and this is some number theory that you could even prove this. If I take a power of x to some n in that is co-prime to p minus 1, I'll get another primitive root. And the way to get back is to take another power. And those powers are exactly the elements that tell you how to translate from one logarithm to another. And they'll always be invertible mod p minus 1. And so that's, another way that you can see. It's actually a better way that you can see that when you take a power that's not co-prime to p minus 1, where 2, if your base p is odd, will not be co-prime to p minus 1, because if it's an odd prime, then p minus 1 is even. And so if I square here, very often I will not be able to have a full discrete logarithm. And so that's the thing to be careful about with discrete logarithms. But other than that, discrete logarithms act much the same as regular logarithms. The properties that you would want are all true. Equals log A plus log B. What are the other properties people like of discrete logarithms? I feel like this is it. Log G of G equals 1. How about let's compute this? Why not? Let's compute this. We're not so lazy, are we? Huh? So let's say we have G comma G prime, our primitive. That means that we'll have log underscore G of A equals C, we'll call it G comma G prime, log underscore G prime of A. So what is C G G prime? Well, we can just take, we can exponentiate on both sides by G and see what we get. We'll get A equals, G to the C underscore G comma G prime times log, why is there oh, I see the problem. My bad. Log underscore G prime of A. Well, if you just look at this for a second, this also has the property that you can specialize this. Let's specialize it to be equal to G to the C G comma G prime. It's a bunch of writing. That's what I'm finding. I'm just complaining. I'm just a lazy bones. I found, yeah, C G G prime to the power of, I'm just going to copy paste this because I'm not feeling, typesetting. Do you guys like typesetting? I think it's fine. Well, we want this to be equal to A. So how do we get this element to lead to A? We need this to be equal to G prime. And how do we get this to be equal to G prime? Well, we just take log G of G prime. And this is the familiar relation. Log g of a equals log g of g prime times log underscore g prime of a. If you take power of g on both sides, you get back a. And again, you should always do this with primitive roots, but if you're careful, you can do it with non-primitive elements. You just need the things to be defined, because sometimes, you write these equations and it a priori assumes they're defined, but all of this works out for non-primitive elements as long as the logarithm exists. But when you don't have a primitive element, the logarithm might not exist. And so the things that you want to be true still hold. And so you can do a lot of math that you used to do with logarithms, just the same with discrete logarithms when you're working over a finite field. It all works out. And, and log expresses, basically log expresses an isomorphism here. And it's a deep isomorphism. It's more than a ring isomorphism. It's more than a group isomorphism. It's a ring isomorphism in a sense. And so it's nice that works out. So now let's talk about the discrete logarithm problem, which is where this actually comes up, and which is what a lot of actual cryptography is built on. You can take this for a large prime. How large are the primes we're using? It's at least 1,000 bits. Maybe I'd have to look up this, but I feel like it's 1,000 to 2,000 bits. Maybe it's up to 4,000 now, because it's been years since I've learned this stuff. And you generally do integers modulo prime. We don't do p to the n much anymore because there's various better attacks on this in cryptography. But with this, you often have this thing called the discrete log problem, where given a random g primitive in a random prime p's unit group, Challenger, the issuer, let's say, computes g to the x for some random x in z mod p minus 1. I should put parallels. I should take that away. In this, sends it to you, and you have to, given g comma g to the x, find x. And a lot of problems are built on this. Like you can do Diffie-Hellman just with this. This is not a cryptography video, so I'm not going to talk about it. And the Diffie-Hellman assumption is different from this. It's stronger than this, but not crazy. Is it different? If I'm wrong, let me know. But I'm pretty sure the Diffie-Hellman assumption, let me see if I can think in my head, is g to the x, and you use the homomorphic property. So both people send g and g to the x. Is it stronger? Maybe it's because of the shared key. Yeah, I think it is stronger. Maybe it's not known to be strictly stronger. But a lot of cryptography literally uses a discrete logarithm problem over FP star. It also does it over elliptic curves, curve point groups, where we call it a discrete log, but we don't really have to call it a discrete log because I don't think people often think of elliptic curve, the group law, as being multiplication. They think of it additively. But if you think of it multiplication, it's like discrete log. And we do that over like 256-bit primes. And that could be a video too if you let me know that you want me to talk more about that. So let's talk about an example. Let's talk about the example that last night me and a friend were talking about and took a while to understand, and it took long enough that I decided to cut it from this video. So Akshay Venkatesh, I'm going to link this video in the description, This is actually just a great talk, and it's mostly a philosophical talk, or an imaginary, just imagining what the future could look like and how the notions of understanding mathematics may change in the as we use more reasoning machines, stuff like AI that could formalize things. And he was giving an example that an AI solved this problem. So if you can't solve it, are you better than AI? No, I'm kidding. I struggled with it a little bit. But to solve this problem, he used logarithms in a clever way. He wanted to show that so the problem is, show that if a comma b is two positive integers, not equal to 1 comma 1, you want to show that this isn't constant, that the greatest common divisor. Well, you can show this is not constant if you show that there's a prime which divides it sometimes, but not all the time, because that prime, as n goes to infinity, isn't constant as n goes to infinity. And so you can show that if you show there's a prime p which divides it sometimes but not all the time. And if you do that, then it will sometimes show up in the GCD and it sometimes won't. So you take this equation and you have these two equations. Well, when does a prime divide it? A prime divides it when a to the n plus b equals 0 mod p and b to the n plus a equals 0 mod p, which is these two equations. A to the n equals negative b and b to the n equals negative a mod p. And you can take logarithms. And when you do this, you get n log a equals log negative 1 plus log b, and n log b equals log negative 1 plus log a. And then you can do replacement, and you get a quadratic in n, and then you can make some argument that if you choose your p cleverly, you can choose a p such that p divides ab plus 1. And then once you've made that choice, you can also bound the number of times, the number of n for which there is a solution, and you can work this out. But I'm not going to do that. So you do that if you want. But this is basically just to say that even though I haven't really seen this come up in the work I do, I guess I'm not a number theorist. The logarithms also can be, it can be useful to know that this is a tool in the toolkit of working with finite fields, that you can solve problems using logarithms. Last thing I wanted to talk about is slide rules. When I was writing these finite field stuff, I remembered slide rules, which maybe you don't. I'm going to Google it. Slide rules. Images. You remember these things? The idea of a slide rule is that pre the proliferation of computers and calculators to the masses, you wanted a way to be able to do these fine multiplications with lots of digits. And the way you could do it is you could basically, this is essentially like a log table. And multiplication and division in a log table is addition and subtraction. And so you move, you slide, this middle piece in and out to form an addition or a division. And then you search with the cursor for the answer, and that lets you compute multiplications and divisions. And I know something that, like, if you are doing discrete logarithms, you always land in z minus q minus 1z, which is linear ordered for the most part. Once you get above q, you have to wrap around, which means that you could make a slide rule for finite field arithmetic. In fact, you could make a table using an existing slide rule, if you have one, that just converts. You can use the technology of the slide rule that's already out there, and you can have like a lookup table, probably two lookup tables, one that converts from a finite field element to your like slide rule number, and one that goes from slide rule numbers to the finite field elements, because those would be ordered naturally different. And you could use a slide rule to do multiplications and divisions inside some finite field. And that was cool. And I thought, well, this is probably something that's been done before. And I looked it up, and in 2001, somebody wrote this short note, and I read it, and they talked about how, yes, you can do this. It's not just noticing that this is linear ordered is all you need to notice. It's not a big insight that you can do a slide rule. But as far as I know, nobody's actually done this, and it's not that difficult. That is because all you need to do is write a little bit of code to translate from this scale to mod q minus 1 scale, and like maybe make some interesting choice. Maybe you work with GF 128 or something, or 256, whatever the QR codes use. And you could make a slide rule to do multiplications and divisions. And so if I get my hands on a slide rule, which I asked around and I might in the next few weeks, I'll just do that. Because that should be just a little bit of code. And then you print out two tables and then you have your slide rule and you're done. But if any of you guys want to do that, I think that would be cool too. I would love to see a slide rule for finite fields because as far as I know, nobody's done that. And I think it would be neat. Anyways, this was kind of an odd video, but I think it was fun. Happy New Year. I just showered for the first time in a year. First time this year. And so I hope you guys are enjoying holidays whenever this comes out. Maybe the holidays are over. Sorry about that. Ooh.